All right, everyone. So I'm going to be talking about Lab 2, which is on simple harmonic oscillation, which is like the sinusoidal motion of uh, objects under certain circumstances. So one of those circumstances where you can have simple harmonic oscillation is like a mass on a spring. So what you're going to be looking at is like a mass hanging off a spring, and then you're going to see like if you pull it down and let it go, how it oscillates up and down. Okay. And so the lab starts off by introducing or reintroducing Hooke's law, which you learned last quarter, or at least whenever you took mechanics. And so it just says that if you displace some object by some distance or some displacement x, then the force the spring will feel. I guess if you displace the spring, either way, if you displace the spring by some displacement x, then the force it feels is negative k times x. Okay, where k is just some constant that's different for each spring. So the higher k means stiffer spring, meaning it's harder to pull apart or like push together, right? This part of lab just says that if you just have a mass on a spring hanging, then mg equals kx. Okay, it's a free body diagram, but that part's not super important. This part is important. So acceleration is the second derivative of position. And if we know that F equals ma from Newton's second law, and we also know F equals negative kx from Hooke's law, then we can say that negative kx equals m d squared x over dt squared. And this implies that d squared x over dt squared is equal to negative k over m times x. Okay? But if we want to solve for the position over time, we have to solve this differential equation. And so if you haven't taken differential equations before, how we do that is we literally just guess that the solution we just guess the solution. Because we just know the form and we're like, okay, yeah, I think this will work. So if we take the second derivative of this guess of ours, then we'll find that d squared x over dt squared is equal to negative omega squared x naught cosine of omega t. But we also know that x naught cosine of omega t is just equal to x itself. So this happens to be equal to negative omega squared x. And if we compare this equation with this equation, then we can see that omega squared must be equal to k over m, which implies that omega is the square root of k over m, which is what we see here. And this omega is the angular frequency of the oscillation of our spring. And if we want to find the period of oscillation of the spring, we have to recall that the period is equal to 2 pi over omega, which is equal to 2 pi over the square root of k over m, and this is equal to 2 pi m over k, which matches what they write here. Okay? And so the next part of the lab talks about how to account for the mass of a spring, because so far we've assumed that the spring has no mass, but in reality springs have mass. So I'm not going to go through all of this, but all they do is they say that if we is that we can look at the kinetic energy of the spring with mass if we write dk, some differential kinetic energy, and they write an equation for that, or some they write an equation for that, inequality, or whatever you want to call it. And then they just integrate that over the entire length of the spring, and they find that we have 1/2 m over 3 v squared. And so the important thing to know from this is just that in our period equation, we just add on this m over 3, where capital M over 3, where capital M is the mass of the spring. Okay, and then now we can talk about what the apparatus looks like. So the apparatus is like a spring here, and then it's hanging, off something at the top, and then it has a loop here, and then we hang a hanger off of that, and then we'll hang masses on this hanger. Okay, and then you don't need it for the first part of the lab, but for the second part you do. We have a motion sensor to look at how far the spring moves up and down when it oscillates. Okay, so to start off, you're gonna like hang the spring, and then you're gonna look at wherever this loop here is, and you're gonna look at I guess the center of it, or I guess maybe it doesn't really matter. You're gonna look at the hoop, and you're gonna choose some point, and you're gonna look at how far down that is, because that's your equilibrium position. So in this case, it would be like 49.5 centimeters. Okay, and then you're gonna add masses and look at the position of that loop, and then you're going to calculate the displacement from the position of the loop by just taking the position minus the equilibrium. And then that'll give you the displacement. And so when you add more masses, you're going to look at how the position changes, if it increases over time or whatever. And then you're going to graph that data. You're going to graph like force versus displacement, and you're going to see what that looks like. So maybe it looks like this, maybe it's a straight line, maybe it's more like this. And you're just going to see if your data like matches Hooke's law, which again is F equals negative kx. I realized I drew this kind of a little too far over, but yeah. So yeah, if you're graphing it, maybe it looks like this, maybe it's like this, maybe it's like this. You'll see. We'll see what it looks like, and then you're going to see if that matches Hooke's law. And then the second part of the lab is when you do the actual simple harmonic oscillation. So you're going to put a mass on a spring, and then you're going to pull it down and let it go, and then you're going to see how it oscillates up and down over time. Okay? And then you're going to do that with different masses, and you're going to see if you add more mass, does that increase the frequency? What does it do? Does it decrease it? Does it do anything at all? And then the last part of the lab is, or I guess, but before I get into that, just you're going to be fitting your data according to a sine curve, because we said that simple harmonic oscillation looks sinusoidal. Okay? And so then the last part of the lab is that you're going to compare frequencies, or not frequencies. You're going to compare periods when you assume that the spring doesn't have mass, and when you assume that the spring has mass. Okay? And so if you remember, the period is proportional to the square root of m over k. Okay? If we scroll back up just to double check that. So we said that the period is proportional to the square root of m over k here, right? And so this is assuming the spring doesn't have mass. But now, if we assume the spring has mass, then our period is proportional to m plus capital M over 3 over k, where this capital M over 3 is our B in this fit. So you're going to fit the data using these two different fits, and you're going to see how they differ. And then, so that's pretty much it for the actual lab part. But then there's these 3 questions at the end. 3.1 is just sort of definitions, like when is Hooke's law valid? What is simple harmonic oscillation? And 3.2 is saying that you'll notice that like when you do your spring data, you'll notice that like your object, like when you let go, like when it's on the spring, it moves up and then down over time, but the amplitude of its oscillation is going to decrease over time. And so that's called damping. And so it's like, where does this damping come from? How do you account for it in your data, like in your fits and stuff like that? And then 3.3 is like, what would happen if these experiments were performed in zero gravity? So if we have an object, like if there's no gravity, then if I pull the object down and let go, like does the object just stay there, or does it move back up normally? Like, is anything different? Just you're going to be answering that question. All right. So I look forward to doing this lab.